It is my pleasure here now to open this session about international projects, and we will start with the European perspective, which has turned very global, really, thanks to the speaker himself, which is Jean-Claude Gascard. He is a director emeritus of research of the CNRS in France. He's also a professor at Université in Paris. He has been a long time interested in the Arctic and the Arctic Ocean. And he has been the king and the president and the prime minister and the lab assistant and the captain and everything in between, among them, or first and foremost, the chief scientist of Damocles, the European biggest IPY project, and it has been my pleasure to serve under him for 5 years in that project. It's been gigantic. I'm sure you will talk something about the numbers when you get up here. But we could never have done it without Jean-Claude, and I just welcome you up to take the stage.
Good afternoon. It's getting a little late, so I will try to go as quick as possible. 20 minutes to tell you a long story involving a lot of scientists. The title of my presentation deals with the climate change, the Arctic Ocean, and the European community contribution during the 4th International Polar Year. In fact, this is my list of co-authors, if I may say so. I couldn't find another way to put them on the board. More than 100 PIs in more than 10 European countries, including Russia. Very soon after the start of this project, in late 2005, we started to investigate about different ways to improve the cooperation in a robust way, not only by words, but by signing memorandum of understanding and establishing solid cooperations involving sharing logistics, instrumentations, fieldwork activities, and data exchange, workshops, etc. Life as usual. And these slides summarize these what we could achieve in the framework of this Damocles project with solid cooperation with the United States via this Search for Damocles project. Russia was already embedded in the original consortium of Damocles. We were also able to sign a memorandum of understanding with the Polar Research Institute of China in Shanghai in order to participate to the China 2008 expedition in the Arctic on board the icebreaker of the Geelong. We had also established a cooperation with Canada with the Polar Continental Shelf Project, and also Environment Canada by investigating a little bit in the Alpha Ridge from the Eureka polar stations, and also some collaboration with the JAMSTEC in Japan for some of the new technology and the new instrumentations that we have used during this project. On these slides, I just summarize remarkable situations. That was the 2nd year of the International Polar Year. I just plugged 7 icebreakers operating at the same times. I probably should have added the Healy from the US. Those icebreakers had a tiny link in each of them, and that was the Damocles project. And this is a situation that we would like to find a way to maintain in the future. I will come back to that in the next slides. The original experimental design of Damocles was well established before the project started at the end of 2005, and this was based on 20 years of observations for the Arctic drift, the sea ice drift, based on the International Arctic Buoy project. And we strictly based the design of the experiments based on the statistics that were very robust, but not valid anymore, like we discovered soon after during the first year of the project. On these slides, I just show the drift of one ship, Tara, that was frozen in ice not very far from the Fram, more than 100 years before. And these represent the first year of the Tara drift in the Arctic, compared to 3 years for the Fram, more than 100 years ago. And this acceleration in the drift was also confirmed when the North Pole Russian drifting station 35 was deployed in September 2007 here and drifted in less than a year, 10 months exactly, compared to something like 2 years for the Fram. Not only the ice drift surprises us, but also the ice extent. And we have seen a lot of different slides. This is another one taken in September 2007 and showing the two icebreakers, the Polarstern from Germany and the Academic Fedorov from ARI in St. Petersburg, trying to find desperately a piece of ice to respect the design of Damocles and other things that were accepted before, but no ice. You could sail this year from Tiksi in Siberia to Tuktoyaktuk in the Mackenzie Delta without seeing any piece of ice. And finally, we had to reconfigure the whole deployment of these ice-stated platforms and other instruments, the polar ocean profiling system, the ice mass balance, and many, many other instruments we had to adapt. This is also something you have seen many times. This is just another way to show the surprise with the large drop in 2007 with a sea ice minimum extent of about 4 million square kilometers, way below the previous record minimum in 2005 and far away from the IPCC predictions. There is a 25 years time lag there between the observations and the model predictions. It was not only about the extent, it was also about the ice thickness, but these we knew before we started Damocles, because those data were collected and published at the end of the 1990s by Drew Rothrock and colleagues, and based on the CISEX expeditions with a submarine under the ice, and measuring thinning of ice from more than 3 meters to less than 2. These we knew, and it's important to keep the chronology right. Sea ice thinning has been discussed as the first important change in Arctic sea ice before anything else. And this is important to keep in mind, and that will come in the conclusions. And we have seen these slides at least twice today, less than 1 hour ago, during the presentation by Dave Barber. And this morning, I think Peter Schlosser showed that, also showing the drastic reductions in the old ice, the multi-year ice in the Arctic. But there are more striking things than these decrease in multi-year ice. There is also this huge replenishment of first-year ice, new ice, and second-year ice in blue that doesn't appear in 2007 and 2005. This is still puzzling. I want to discuss that a little bit on these slides and the slides after, showing a way to follow these multi-year ice evolutions through a seasonal cycle. You see on the blue crosses here the decrease of multi-year ice just by ice moving through Fram Strait and leaving the Arctic forever and melting away in the North Atlantic. So this is a decrease every year by something like 2 million square kilometers. And you see this ramp is pretty consistent. Sometimes there are some bump here, like in 97, but over these 10 years periods, the system looks very regular. And something happened during the 2000s. This is a study that we started with the European Research Satellite with a team at Ifremer in Brest. And this was continued with QuickScat. Is it the change of satellites that reduce the amplitude of these respiration? But the main fact is here. In 2005, which is the first minimum record before 2007, there was like a stroke. I mean, there was no replenishment. The replenishment is at the end of the summer when what's left as far as multi-year ice is concerned is supplemented by the first-year ice that survived the summer melt. And you start again with this. This is how you can supply and replenish the multi-year ice that has leaked away during the winter. And that's the only way to fabricate, to build up the multi-year ice in the Arctic. But here, there is no replenishment. And even more striking, in 2007, which corresponds to the second minimum, this is work done by Ron Kwok at JPL, there was also no replenishment of first-year ice. So you see we have these years where, like in 2007 and 2005, the multi-year ice is not replenished by the first-year ice, which has either melted away completely or disappeared through Fram Strait or the northern Barents Sea. And you have the other years, like 2008 and 2009, where you have a huge replenishment of sea ice for reasons we have to understand. But this is still a question today. What we have tried to do during these Damocles and related and involving all these international cooperations that I mentioned before was to set up two kind of, the observing system was based on two main elements. One was what we call the Lagrangian elements. You deploy something on ice or in the water and they drift with the currents or with the ice and this is a so-called Lagrangian. This is what we use most of in the Central Arctic. The other part is the Eulerian framework, and this is based on moorings and instruments which are fixed in space, and you are measuring the same elements as far as physics is concerned, but in a different framework. I must say, just as a message to deliver, that we were quite successful. And when I say we, it includes Damocles and all our partners. We were quite successful in the Lagrangian part of the experiments. And except the Fram Strait, which is a continuing process, everything else we did, deploying moorings along the continental slope were upset by either technical problems or excess of ice in these regions. Also, I want to stress your attention on the I think, a very important element for the future in designing sustainable Arctic observing network is the capability for the Lagrangian systems to transmit the data in real time. And time is an issue where you have to work both in the atmosphere, ice, and oceans. You can't wait months or years to merge the data and understand what's going on there. In addition to these drifting autonomous platforms, we also were able to have organize this Tara drift. This was the first drift of a ship like that after the Fram, and following the same spirit. I want to point out on this graph the importance of this profile, which is temperature from the upper atmosphere to down the ocean here. You have a huge warm air masses here. It's more than 10 degrees at 800 meters altitude. And the only thing which keeps the ice, we are July 2007 and near the pole for this particular instant. And I want to stress your attention to the fact that the only element which keeps ice from melting is this upper ocean layer. Indicating of the importance of the oceans in keeping ice from melting. That's the summer situation. As a result, I have to go quickly through the conclusions now. As a result from the 2 intense years of observations during the IPY, we just collected all the data we had as far as the CTD, conductivity, temperature, depth profiles are concerned. I show this, the distribution in space, and this is now the distribution in time. So this reminds me of this kind of curve that we used to draw before starting the IPY, expecting something like that. But now the problem is to avoid the curve to go down again. Well, I must say that at this stage we have not been able to collect all the most recent information, but it will be difficult to maintain this rate of collections. And this is important. I just showed the temperature profile in the atmosphere, in the oceans, to understand what's going on with the ice. You have on these graphics the distribution on the TS plots of the Pacific water. This is a TS diagram. This is to index for depth at 50 and 80 meters. So you see these, the allocline and the thermocline. This is the typical distributions of water masses, and with the Atlantic water, which is sitting down below here, far away from the ice, and the Pacific influence here. This study is presented in a poster that I advise you to look at, and presented by Pascaline Bourguin. She's a PhD working on that data. And from this array of this collection of information, it's becoming reliable now to estimate the influence of the Atlantic water versus other water masses, and we can do the same with the Pacific water and the allocline in between. Another study, this is for the oceans. So now for the atmosphere, and this is a work done with Elena Maximovich. There's 2 posters outside too, showing the decrease in the intensity of the cold in winter. This is based on the NCEP reanalysis and ERA interim. So be careful, the red here is the cold, very cold. And so it's becoming more pale in these in recent years. And this is the same way to show the decrease in the number of freezing degrees days over the winter from September to May the following year. Like there is a loss of something like almost 2,000 degrees, freezing degrees days, to explain the thinning of the ice. it's not only the intensity of the cold, it's also the surface, the area over which it is acting. And you see that two different years here indicating the same intensity of cold, but applying in much different areas. From that, I just want to, before showing the last slides, indicate that we can build up a winter index, which is just the integral of the cold and times the surface over which it applies. And this index proved to be very useful in the sea ice outlook predictions for predicting what's the minimum summer sea ice minimum will be the following September, several months in advance. As conclusions, I would like to summarize by saying that Arctic sea ice has changed, and by many accounts, like it's not only the extent, it's also the thickness that started to decrease a long time ago. The drift has accelerated by a factor of at least 2, and the ice is becoming younger and younger. But all these sea ice elements are interrelated, they are not independent. It's still puzzling to realize that the extreme sea ice minimum in 2005 and 2007 were characterized by a quasi-disappearance of first-year ice and second-year ice, resulting in no replenishment of multi-year ice. In contrast with 2008 and 2009, where still multi-year ice reduced drastically, but the first-year ice and second-year ice was spreading widely in the Arctic and compensating for these multi-year ice reductions. The thinning, that's very important, of sea ice started a long time ago. As reported, when you look at the literature, you will find the first alert as far as sea ice is concerned, based on the sea ice thickness. And it was mentioned several times today that sea ice thickness is really an important component there. We can also say that the long-term global atmospheric warming related to greenhouse gas effect seems to be the triggering process for that. Otherwise, we have to find another arguments, but at least this is a solid one. But the process for explaining sea ice thinning and the reduction that we observe today is the greenhouse effect is not able to explain the whole story. This is because we have this albedo polar amplifying feedback process that is acting very, very sharply. And there is a strong need for looking at the Arctic sea ice thickness distribution and the evolutions in the coming years. Thanks to the cryosat that is planned for a launch in a month or two, I think in addition to that, we have to maintain the in situ observations. I didn't have time to describe all the different technology that were used in these studies, but this has to be maintained, as well as our advance in numerical modeling and space observation. Thank you very much.